Good evening, class. This is the last part of our chapter, light revision, and we had ended the previous video with the ray diagrams for convex lens. Now we will see for concave lens. Now we have just two cases for concave lens ray diagrams. Concave lens are useful for diffracting or deflecting the ray of light. Diverging is the right term. See, the ray of light in first case is coming from infinity. It gets diverged, and when we pull back the ray of light, an image is formed at f1. A diminished image is formed at f1. This is the first case. In second case, the object is kept between in the second case, an object is kept between f1 and 2f1, and one ray of light touches the concave lens and diverges, and its ray diagram is taken backwards. Other one just passes through, and if we take back, a diminished object is formed in front of the lens. Okay, so these two cases are only there in case of a concave lens. Now let us see the sign convention of spherical lens. Sign convention is same as the sign convention used in the mirrors. Rules are applied for signs of distance, but the measurements are taken from optical center of the lens. Okay, optical are taken from the optical center of the lens. According to the convention, focal length of convex lens is positive. Why is the focal length of convex lens taken as positive? Because the focal length is taken as positive for the convex lens. It is at the right side of the lens, f2. That's why the focal length of the convex lens is taken as positive. Now there is one important thing to be remembered by all the students, that the focal length of both convex lens and convex mirror are positive. And this fact is important for solving all types of numerical questions. So focal length of convex lens is taken as positive, and that of a concave lens is always negative in all the cases. Now let's go ahead and see some important formulas such as the lens formula and magnification. If you remember the mirror formula, it was 1 by V plus 1 by U is equal to 1 by F. Same way we see lens formula. U is the object distance, V is the image distance, F is the focal length. So for mirror formula we had 1 by V plus 1 by U is 1 by F. For lens formula we have 1 by V minus 1 by U is 1 by F. Just the sign difference. Okay. Now next we see is the magnification. What is a magnification? Magnification produced by lens is similar to that for spherical mirrors. It is the ratio of the height of the image and the height of the object. So magnification formula is same for both mirror and lens. Magnification is also related to object distance U and image distance V. So magnification is h dash by h is also equal to V by U. In case of mirror it was minus V by U. In case of lens it is V by U. I encourage students to memorize all the formulas, both mirror formula and lens formula. Mirror formula is 1 by V plus 1 by U is 1 by F. Lens formula is 1 by V minus 1 by U is 1 by F. Okay. Let's go ahead. Now we come to the last discussion based on this chapter, that is the power of lens. Power of lens. Okay. So whenever some student or some person has problems in looking at objects, they usually go to a doctor. They give them some power lens, like they will give them some glasses. Glasses will have some power. So doctor tells us, okay, this is your power of the lens. This is the power of the lens. So what actually is the power of lens? Let us discuss. The ability of a lens to converge or diverge light rays depends on its focal length. A convex lens of short focal length bends the light rays through large angles and focuses closer to the optical center. A concave lens of very short focal length causes higher divergence than the one with longer focal length. The degree of convergence or divergence of light rays by a lens is expressed as its power. Now, what is the power? There is a mathematical formula to calculate the power. P is equal to 1 by F, where P is the power in diopters. What is the unit of power? The unit of power is diopter, and F is the focal length in meter. Power of lens P is defined as the reciprocal of its focal length. The SI unit of power of a lens is diopter. One diopter is the power of lens whose focal length is 1 meter. Such question can be asked, define one diopter of power. So one diopter power of a lens is a lens whose focal length is 1 meter. So one diopter is the power of lens whose focal length is 1 meter. Simple. Now, the power of convex lens is positive. Why? Because convex lens always has a positive focal length. So, power of convex lens will be positive. And that of concave lens is negative. Why? Because the focal length of concave lens is negative. Now let's see the last thing. Opticians prescribe corrective lenses indicating their powers. It is more convenient to use powers instead of focal lengths. A lens of power plus 2 diopter has focal length of 0.5 meter. Understood? Because if you put 0.50 meter focal length, you get power as 2 diopter. The lens is convex. So if in a question they say that plus 2 diopter is the power of lens, what is the nature of lens? It is convex. Lens of power minus 2.5 diopter has focal length minus 0.40 meter. Lens is concave because power is negative. In many optical instruments, in many optical instruments, several lenses are combined to increase magnification and sharpness of the image. So the net power of the lens placed in contact is the algebraic sum of the individual powers P1, P2, P3, P4. See, if these are all kept together, it is the power of the lens can be calculated by adding or subtracting. Plus 4 minus 2, 2. Plus 6, 8 minus 4, 4. Okay, like that. So you will get 4 diopter as the power. Here also, if you see 8 and minus 8 and 4 minus 4. 2 and minus 6 minus 4. 0 and 6 is minus 4 minus 4. Same way here. 0 plus 4 is 4. Minus 2 plus 6 4. Minus 4 plus 8 is 4. So plus 4 diopter lens is a convex lens. Minus 4 diopter lens is a concave lens. Okay. Let's move ahead and see the power of lens. During eye testing, an optician puts several corrective lenses of known power inside the testing spectacles frame. Thus, the required power of the lens is calculated by algebraic addition. Example, 2 lens of power 2 diopter and plus 0.25 diopter is equivalent to single lens of power 2.25 diopter. Simple additive property of the powers of lenses can be used to design lens systems to minimize certain defects in images produced by a single lens. Such lens system is commonly used in the design of lens of camera, microscope and telescopes. Okay, the simple additive property of power of lens, where is it used? It is used to design lens systems to minimize certain defects in images produced by a single lens. Such a lens system is commonly used in the design of lenses of camera, microscope and telescope. So with this, we come to the ending of the chapter. The chapter is ended by the discussion of the power of a lens. So in this chapter, the chapter light, reflection and refraction, we have learned so many things. We first started learning about the spherical mirrors, concave, convex mirror, the different terminology related to both the mirrors, the types of concave and convex mirror, where are they used, what are the uses, what are the ray diagrams, very important ray diagrams. Then we went forward and we learnt about refractive index, how to calculate refractive index, what are the different refractive indexes of different materials, the numericals of refractive index. Then we went ahead and learnt about lens, both concave and convex lens, the ray diagrams of convex and concave lens. And then we also read about the last topic, that was the power of lens, that is P is equal to 1 by F, where F is focal length in meter and power is calculated in diopters. So with this, we conclude this chapter, and I really hope these videos were helpful for the revision of our students. Thanks a lot.